So when you will open the files that you downloaded, in this example folder there will only be the input.dat. Then after you compile the DETO program, you will copy the executable DETO2D. And this is what we saw in a previous lecture. These other files are actually produced when the simulator runs. In this case, I've already run a simulation and I will use these data, this output, to explain to you what kind of output to expect and how you can tell the code what kind of output you want it to produce. So the first output is this log file. The log file is just telling you if anything went wrong during the simulation. It gives you some information of what might have gone wrong, but not always you get the information that you want. So it's a file that is marginally useful for you. The useful files are the others, are thermo, all dump, and DETO2D. Well, DETO2D is the file that will give you, that you can open with this program Obito that we will learn later, and will allow you to see how the structure is evolving during the optimization. So to show these videos, and then when you have this kind of output, you can actually create pictures, create videos, and we will see all of these in later videos. All dump is similar, but instead of just showing you the optimization, it also shows you the deflections of the beam. So in this case is this file here that also shows you how the structure is progressively deflecting before redistributing the sheaves. Okay? So it's the complete deflection and optimization output. This is the file, this all dump is the file that you can turn on or off, that you can request the code to produce or not by setting this to yes or no. So if you put this equal to yes, the code will produce this file. If you put this equal to no, the code will not produce this file, all dump, but it will still produce the DETO2D, which is how the structure is evolving, how the shear in the structure is changing during the optimization. Of course, because the DETO2D only contains the shears, and the all dump also contains all the deflections, the DETO2D, as you can see here, is smaller, in this case 6 megabytes, compared to the all dump that is much larger. It's 10 times bigger, approximately. Then two other files that are very useful are the thermo and the thermo. A thermo file is a file that contains thermodynamic results. So it contains information such as what is the value of the cost function, that in your case is the energy of the system, the strain energy, during the optimization process. What is the total shear, the sum of the shears in all the structure? Is it agreeing to the target F that you want, or is it away from the target F that you want? This kind of information is contained in the thermo.txt. Other things that you can add to the thermo.txt are things like displacements or forces on individual particles. And this is very useful because, for example, if you want to create the force displacement curve, like we showed in previous videos, well, you need the code to give you the forces and the positions of the particles for which you want to compute the force displacement curve. So, for instance, in this example, we know the displacement. We are imposing the displacement, and we are imposing the same displacement to all the particles from 885 to 892. So if we want the force displacement curve, we need to plot the vertical position of any of these particles here. Because if we know the initial vertical position and the vertical position at the end of a minimization of an optimization step, then the difference of the two will give us the vertical displacement. And this is the value y, so we are adding to the thermo the y position of the particle 888. Okay, so this is a quantity, this is monitoring the value of the vertical position of this particle. At the end of each optimization step, we expect this to be 0.4 millimeters below the initial value, because this is what we are imposing at the displacement. So hopefully, if it works, we should get 0.4. Then we can add other things like the forces. If we want to draw a force displacement curve, then we definitely want the force applied to all the particles that we are displacing. So you see that other things that we are adding to the thermo output is the force in y direction for particle 885, 86, 7, 8, up to 92. So all the particles to which we are imposing a displacement, we want to read their corresponding forces. And by doing this, we are ensuring that these forces will be recorded as output. Now, in the next video, we will run the simulation and we will check the output, so we will get an idea of what exactly the code is producing and how we can extract information from those.